All right, today we're playing detective. We've got a real chemical mystery on our hands. Imagine you take a simple powder, you heat it up, and poof, more than a third of it just vanishes. So, where did it go? Let's dive in and solve this thing.
Okay, so our story starts with something you almost definitely have in your kitchen. Yep, good old sodium bicarbonate, or, baking soda. Looks like a simple white powder, right? Well, it's holding on to a really fascinating secret.
I mean, we all know this stuff is a total star in the kitchen, right? You mix it with something acidic, like lemon juice, and boom, you get carbon dioxide gas. Those are the bubbles that make your pancakes so light and fluffy. But here's the key. That reaction needs an acid to kick it off.
And that brings us right to the heart of our mystery. What if you take the acid out of the picture completely? What happens when you just heat it up, all by itself, no other ingredients, just pure baking soda and a flame? What's going to happen then?
So, this is where we get our hands dirty, so to speak. We're going to run through a pretty standard lab experiment. Heat up some baking soda and just watch what happens. But trust me, the result is, well, it's a real head-scratcher.
The setup is super simple. First, you carefully weigh out your starting amount. Then, you heat the sample in a test tube for about 5 minutes. And then, this part's super important for safety and for getting good data, you let it cool all the way down. Once it's cool, you weigh what's left.
Okay, let's get our numbers straight. Here's our starting point. We're beginning with exactly 7.50 grams of baking soda. That's our baseline. So lock that number in your brain, 7.50 grams.
And here's the result. After all that heating and cooling, the final mass is down to just 4.73 grams. Whoa, that is a huge change. This isn't some tiny measurement error, no way. Something really fundamental just happened inside that test tube.
Let's just stop and think about that for a second. Over 35%, more than a third, of the original stuff has just vanished. It's not like we spilled any or scooped some out, it's just gone. So I'll ask again.
All right, time to put on our detective hats. To solve this, we've got to dig into the chemistry. We need to figure out what actually happened to that baking soda when we turned up the heat. So there's a name for this process. It's called thermal decomposition. Thermal obviously means heat. The energy from the flame is literally breaking the chemical bonds apart. And decomposition, well, that's because our one compound is breaking down into a few simpler things. The key here, though, the atoms themselves aren't being destroyed. They're just getting rearranged.
So if we write this out as a chemical reaction, here's what we've got. Our baking soda, the NaHCO3, breaks down into sodium carbonate and water. But wait a minute. Look at those question marks. There's still something missing, another product that we can't see. A huge piece of our puzzle is still unaccounted for.
Okay, so to find this missing piece, to finally crack the case of the disappearing mass, we have to bring in one of the biggest, most fundamental rules in all of science. Seriously, this law is the key that unlocks this entire mystery.
And that rule is the law of conservation of mass. It's an unbreakable law of the universe. It states that matter, mass, cannot be created or destroyed. It can only change form. So the total amount of stuff you start with has to equal the total amount of stuff you end with, period. No exceptions. It can go from a solid to a gas, sure, but it can never ever just cease to exist.
So you see the problem here, right? We have a conflict. Our scale is telling us the mass dropped, but this fundamental law of physics is telling us mass can't be destroyed. How can both of those things be true? How do we make sense of what we saw with our own eyes versus this unbreakable rule?
The answer, it turns out, is all about accounting. We just have to account for every single atom. And the tool for that job is a balanced chemical equation. It's kind of like balancing a checkbook, but instead of dollars and cents, we're tracking atoms.
And when we do that, atomic accounting, bingo, we find our missing product. That mystery substance? It was carbon dioxide, CO2. So now we have the full picture. Our baking soda decomposed into 3 things: sodium carbonate, water, and carbon dioxide. In this table right here, this is the proof, the smoking gun. Look on the left side, the reactants. We started with 2 sodium, 2 hydrogen, 2 carbon, and 6 oxygen atoms. Now look at the right, the products. You add them all up, and what do you know? 2 sodium, 2 hydrogen, 2 carbon, and 6 oxygen. It's a perfect match. Not a single atom is missing. They just got shuffled around.
The mass was conserved the whole time. So here's the big reveal, the solution to the whole mystery. The mass wasn't lost at all. It just changed form. That lost mass didn't vanish. It escaped out of the top of the test tube as invisible gases, specifically water vapor and carbon dioxide. So yeah, the solid left behind weighed less, but if you could have trapped and weighed those gases, the total mass would have been exactly 7.50 grams. Mystery solved.
Okay, so we've cracked the case. But let's zoom out for a second. What are the big takeaways here? What did this seemingly simple experiment really show us?
Well, first off, we've seen that the law of conservation of mass isn't just a suggestion, it's always in effect. Second, we learned that those balanced chemical equations aren't just for homework, they're how we balance the books for matter. And maybe the coolest part, we proved that gases have mass. Even though you can't see them, they have weight. And finally, it just goes to show you that a simple experiment can reveal a truly fundamental law of nature.
Now I gotta say, while this experiment is cool, lab safety is absolutely key. Anytime you're working with a Bunsen burner and hot glass, you have to be careful. Letting things cool down completely before you touch them is non-negotiable. And hey, here's a little pro tip. That part about covering the test tube while it cools, that's not just for kicks. It actually stops the leftover solid from sucking water vapor out of the air, which would totally mess up your final weight.
And that leaves me with one last question for you to chew on. We just proved, without a doubt, that invisible gases have mass. So think about the air in the room you're in right now. All that nitrogen, all that oxygen, it all has weight. My question is, how much do you think it weighs? The answer is probably a lot more than you think.